Hi, welcome back. So you might have wondered how your TV remote works. Well, when you press the buttons, you're actually transmitting infrared radiation to your television, and that's what controls the station and the volume and so on. We're going to use infrared radiation to understand how infrared spectroscopy works in this lesson. Okay, so in this lesson we're looking at infrared spectroscopy. The study design points, we're looking at the identification of different covalent bond types, and we're going to do that by using qualitative infrared spectroscopy data analysis using characteristic absorption bands. And you will need to use your data book for this. So if you get your data book, that will make it easier for you. Okay, so what is the infrared radiation or infrared light? It is this section of the electromagnetic spectrum. It's all the way from really small, really short wavelength but high energy X-rays, so short wavelength, very high energy, through to X-rays, then UV light, which is the light from the sun that can burn our skin, to visible light that we can actually see. So here you can see the Roy-Gabiv visible spectrum. Infrared radiation has a longer wavelength but lower energy than visible light. And it's called infrared because it continues on the spectrum near what we can see with red light in the visible spectrum. All covalent bonds are comprised of shared electrons that are constantly on the move and are moving. So all covalent bonds actually vibrate. So they bend and they stretch. They bend, they stretch, they wag. There's an animation attached to this that you can have a look at to look at the various shapes. What infrared radiation is changes the vibration. And it's the changes in those vibrations that are picked up on an IR spectrum. Okay, so let's start off with looking at the principles of infrared spectroscopy. First of all, it's a qualitative analytical technique. It's used to identify the types of covalent bonds and functional groups that are present in organic molecules. It doesn't give any idea of the quantity of those. The second thing is all covalent bonds, as I mentioned, have a natural vibration, so they're moving all the time. And in infrared spectroscopy, we're using infrared radiation, like the remote control for your television, to make changes to the bond vibrations. And these changes are measured on an infrared spectrum. You don't need to know how the infrared spectrometer works. What you need to be able to do is interpret the spectrum. Such as the example that's shown here. Now, in this spectrum, on the x-axis, we have wave number, which is the reciprocal of wavelength, and it's measured in centimetre -1. On the y-axis, we have transmittance. Now, transmittance is the opposite of absorbance, and we're actually reading the IR spectrum from the top coming down. The lower down the peak or the band, the greater the absorbance. So this is an absorption band. There's another bit here. There's a bit here. And you can see other fragments. These are all absorption bands, and they're what's measured on the infrared spectrum. So it's a graph that represents the absorption of infrared light corresponding to different wavelengths within the infrared part of the electromagnetic spectrum. The next thing to know is that in VCE, we're concerned about this part of the spectrum from 1500 to 4000 centimetre -1, and we read it from right to left. So this is the part that we're focused on between 1500 and 4000 centimetre -1. And what we do is we compare the absorption peaks of our spectrum with the ranges listed in the VCART data book. Now, the section that I've blacked out here, or read it out, from 400 to 1500 centimetre -1 is called the fingerprint region. And it's called that because it's like every organic compound has their own unique fingerprint. So this actual complicated set of peaks that we can see here, that's all indicative of a particular compound. So ethanoic acid versus propanoic acid versus butanoic acid, for example. In past exams, Vika has labelled important information in the fingerprint region, and that's not the main focus of what you need to be able to do. You need to be able to identify information from 1500 all the way to the left to 4000. Continuing with the principles of infrared spectroscopy, here's an example of an infrared spectrum. The sorts of things that you need to be able to explain are using the terms strong, which means very vertical, medium, about halfway, weak, which is close to the top, broad, which is a large wave number range, narrow or sharp, which is a reduced wave number range. They're the sorts of terms that you need to be able to describe the patterns that you see at particular wave numbers. Okay, so the most useful part of infrared spectroscopy that we can use is the identification of functional groups or specific covalent bonds within molecules. And if you look at the data book, you see that there are lots of carbonyl compounds containing C double bond O that have wave number ranges. They tend to be quite narrow ranges. And if you need to identify something from a spectrum, you need to label it as the carbonyl and the type of carbonyl. Is it from an amide, an aldehyde, an acid, a ketone, or an ester? So there's 5 different types of carbonyl groups. Now, if we have a look, the peak that we've got here is from about 1650 to about 1720. So it's a carbonyl, but we would then try and look at our data book, and maybe we would call it carbonyl aldehyde. We find that the best correlation that we can. Now, the wave number range corresponds to the change in vibration of particular covalent bonds. So when the sample is in the IR spectrometer, the infrared light is changing the vibration, and that's what we're picking up with the signal. Making sure that for carbonyl environments, we specify the type, so whether it's amide, aldehyde, or acid, for example. Okay, now the CH bond, very common in organic molecules. And if we have a look at the data book, you can see that a carbon single bond hydrogen group that's in alkanes, alkenes, and arenes, which are sort of benzene rings, have a wave number from 2850 to 3090. So that's this section here. So that's the CH bond. Now we can see that there's another couple of signals here and here. They'll be due to something else, but most organic compounds will have at least one narrow, sometimes sharp, sometimes medium peak to indicate the presence of a carbon-hydrogen bond. So just remember that most molecules, you'll see that. Okay, so here we've got a spectrum with a number of covalent bonds labelled. We've got a carbonyl group, and then we can sort of specify which type of carbonyl it is. We've got our carbon to hydrogen stretch for our single bond carbon-hydrogen. And over here at around 1620 to 1618 centimetre minus 1, we've got a carbon to carbon double bond. And again, it's quite narrow and deep or sharp. We've got other bonds present. In this case, we've also got an OH, and we'll talk about that in the next slides. Okay, so there are 2 groups of OH bonds that you need to consider. They're OH acids and OH alcohols. So the OH alcohols, we're talking about hydroxyl groups, but the OH acid, we're talking about the carboxyl, and they've got different wave number ranges. Now, the carboxyl acid, the carboxyl group, the OH in the carboxyl, is a whole 1,000 centimetre -1 range, which is very broad. Whereas the OH alcohols, which we'll look at in the next slide, are narrower. Now, we've already recognised that around 2,800 we've got a carbon to hydrogen stretch. But if we look at the whole width of this, it goes from about 2,500 to 3,500. So this is the OH acid stretch. It's a medium, it's not as deep, but it's very broad. Okay, now we're looking at OH alcohols, so hydroxyl groups, and we can see that that's a narrower range and further shifted to the left than OH acids. It goes from 3,200 to 3,600. So that's about from here to here. This is the OH, and you have to say alcohols in this case. This peak around 3,000 is the carbon to hydrogen stretch. The OH alcohols is broad, not as broad as OH acids, and in this case it's a bit stronger than the previous spectrum that we looked at. Okay, NH bonds overlap some of the area that the OH bonds do. NH bonds are found in amines and amides. The clue for this one is checking to see whether our nitrogen is an element. Now we've got our CH stretch, and then here we have our NH amide or amine stretch. So it's not as broad as the OH alcohols and the OH acid. It's only over 200 centimetre -1. Okay, let's look at a worked example. We've got an unknown organic compound and we know its molecular formula is C4H8O. We're told that it's non-cyclic, in other words, it's a chain molecule, and contains a double bond. The infrared spectrum is shown. What does the region 3,100 to 4,000 centimetre -1 indicate about the bonds in this molecule, and give your reasoning? Well, if we have a look at 3,100 to 4,000, we've got a very weak signal here. We really don't have much absorbance at all, so we say that there's a peak that is absent from 3,200 to 3,600, or to 4,000. And when we look at the data book, we see that the alcohols, we would expect to see an OH alcohol stretch 3,200 to 3,600 -1, and that's actually empty. So it's the absence of an absorption band at 3,200 to 4,000. So that means that we don't have an OH alcohol stretch. This weak signal that we've got around 3,000 is our typical carbon single bond hydrogen signal. So that is what this weak signal is. So because we don't have an OH alcohol, we can say that the compound is not an alcohol. So let's summarise what we've learnt in this lesson. The fingerprint region is the section that's least useful in VCE. That's the range between 400 and 1,500 centimetre -1. It's okay if we could overlay the spectrum onto a database, we'd be able to identify a particular molecule, but it's not seen that often in VCE exams. It's hard to assign absorption bands in that fingerprint region because there's a lot of up and down going on. From the region of 1,500 to 4,000 centimetre -1, that's the region that we're most interested in for VCE. And you need to be able to describe the type of absorption band or peak in that region, whether it's strong or most of the way down, medium about halfway, or weak just at the top. You also need to describe the width of the band, if it's narrow, a short wave number region, or whether it's broad. Sometimes the peaks overlap as well. And you need to correlate what you see or don't see on the spectrum with the wave number ranges from the data book. The wave number range corresponds to that change in vibration of particular covalent bonds at particular wavelengths. So here we've got an OH group, and you would specify whether it's alcohol or acid. We've got a CH stretch, we've got a carbonyl group, and we would specify the type. And we also have a carbon-to-carbon double bond. So it gives us information that we can start piecing bits of a puzzle together. Okay, see you next time. Bye.